Thank you, Meghna, for the introduction and for hosting this webinar. And hello all. In today's agenda, we will discuss about quantization, what and why, key terms to be known for this lecture, visualization tools available for TensorFlow models, distribution channels available for Intel optimization for TensorFlow, introduction to Model Zoo for Intel architecture with a demo, introduction to Intel AI Quantization tools for TensorFlow with a demo, and then finally, inside the black box of Intel AI Quantization tools for TensorFlow, if time permits, with a demo. Before we dive on even further, here are some few key terms that you might want to know to have a better understanding on this lecture. I would pause here for like 30 seconds so that you could go through and understand a few key terms. I hope you got a sense of some terms. Let's dive in. The first part of this webinar is post-training quantization. What it is and why do we care? What is low precision or quantization? Computers have a finite number of bits to represent infinite real numbers. How accurately we represent them is decided by how many bits we use. A 32-bit floating point, in short FP32, as you guessed, has 32 bits, being the default for machine learning applications. With smaller data types such as Int8, which has 8 bits, these numbers are quantized, that is discretized to some specific values, which we can then represent using integers instead of floating point numbers. The diagram on the right, the orange line depicts the FP32 numbers, which is then mapped, that is, or quantized or discretized to Int8, which is the blue line. Why do we care? Arithmetic with lower bit depths is faster. 32 bits to 8 bits equates to 4x reduction in memory and can also squeeze more data into caches and registers. Fixed point arithmetic is faster than floating point arithmetic. Why does it work? It just so turns out DNNs are quite robust to noise once trained, meaning subtle round-off numbers still produce reasonable accurate answers, meaning reasonable accurate predictions. Weights and activations for a layer also tend to lie in a small range, allowing us to concentrate the fewer bits that we have in Int8 with reasonable accuracy. I hope you understand what quantization is. But what is post-training quantization? It's just that the model that is trained in FP32, after training, is taken and converted to Int8 data type, and hence the post-training quantization. Here at Intel, we wanted to make your out-of-box experience for running a TensorFlow model or even quantizing it very intuitive and easy. It is for this purpose that we provided several tools and guides to get you started. To start with, Intel optimization for TensorFlow is made available through several distribution channels. You can find the installation guide at software.intel.com, articles Intel optimization for TensorFlow installation guide. Here, we guide you to how to install Intel optimization for TensorFlow through Anaconda or pip wheels or even Docker containers, or you can build from source. Visualizers help us to really visualize TensorFlow models. There are several available, two of which are mentioned here. One, TensorBoard. Two, Netron. It is to note that TensorBoard is an official Google TensorFlow supported visualizer, while Netron is a third-party open source visualizer. Both of these have been found to be useful in different situations. Like TensorBoard, which is on the left, is more dynamic and where nodes or ops can be double-clicked to open up, like shown here. And each of these individual nodes can be studied in more detail. While Netron which renders the whole graph as a huge file, color codes each of these orbs in different colors, like bias add, ReLU, maxpo, and also color codes all the constants in white, which can be then clicked to view the values inside the constant. We've displayed more neutron graphs for better understanding in the later portions of this webinar. While the distribution channel makes it really easy to install Intel optimization for TensorFlow, we at Intel found that users also required a single one-stop location where they could run the TensorFlow models, be it the FP32 or the optimized FP32, and including Int8 and other future models. Hence, here at Intel, we created one such one-stop location for models, introducing you to Model Zoo for Intel architecture. Here, you could take an FP32 model or an Int8 model, run it in a TensorFlow environment with Intel optimization for TensorFlow for latency, throughput, and accuracy. All this is made easy using Model Zoo for Intel architecture. You can download this at github.com/intelai/models. We've architected this Model Zoo for Intel architecture such that it's very easy to run several models using the same command line template. We generally run a model for three types of runs: a performance run, or latency run, or an accuracy run. For all the three runs, the basic template for command line is the same. You call launch benchmark.py, pass in the graph, either FP32 or Int8 that you want to be run, specify the model name, ResNet50, the framework, TensorFlow, the precision, whether it's FP32 or Int8, or in future, bfloat16, mode as inference, the batch size, 128. A batch size of greater than 1 is mostly associated with a performance run or a throughput run, and a batch size of 1 is usually associated with a latency run. For an accuracy run, we just provide an additional argument, accuracy only, and specify the data location of the dataset that you want the accuracy measure to be run. For ResNet50, it's usually ImageNet. To explain at a very high level how these TensorFlow models are executed using Intel hardware, these FP32 or Int8 protobuf files have a lot of TensorFlow ops. These, when run in an Intel optimized TensorFlow environment using the Model Zoo for Intel architecture, at runtime gets converted from TF ops to deep neural network library ops, which uses the deep neural network library with deep learning boost, which then uses the VNNI instructions in the Intel hardware. A quick look at Model Zoo for Intel architecture at github.com/intelai/models lands us into this page. Clicking on the benchmarks folder and scrolling down, we find that there are several models available. And on the right, it also mentions both the Int8 and FP32 model types that are supported, which, when clicked, also shows us instructions of how to run that specific model. Let us now look at a short demo of how easy it is to run Model Zoo. I have actually spawned an AWS instance here with a configuration Ubuntu Server 18.04 LTS HVM with SSD volume type C 5.12x large. The first step is to pull the Docker container with Intel optimization for TensorFlow version 1.14. You might very well use 1.15 if you prefer. I'm actually pulling it from GCR or Google Cloud Repo. In the interest of saving time, I have pre-downloaded the Models Zoo repo from github.com/Intel AI/models into this directory called webinar. And I have mounted this onto my Docker container. Now I'm inside my Docker container environment. Now I'm navigating to my webinar folder that I mounted and my Model Zoo repo to the benchmarks directory. Now I'm going to run the FP32 throughput using the same command line template, wherein I call launch benchmark.py, pass in the graph freezed optimized ResNet 50 FP32 final, the model name ResNet 50, framework TensorFlow with the precision FP32, and a batch size of 128. You could do the same thing for Int8, where all I need to change is mention the precision to be Int8 and pass in the Int8 final graph, batch size being 128. If you so want to run the latency run, you could just repeat the same command line template with a batch size of 1. From the demo, you can see that the optimized Int8 ResNet 50 model compared to the optimized FP32 ResNet 50 model, when run on an AWS instance with configuration Ubuntu Server 18.04 LTS HVM, SSD volume type C 5.12x large, with Cascade Lake having 24 cores running VNNI instructions, has a latency that is greater than 2x improvement over FP32, throughput having greater than 3.5x improvement over FP32, and accuracy having less than 1 percentage point loss. Such improvements are made possible by using Intel's Deep Learning Boost with VNNI instructions. Next, let's look at post-training quantization steps. That is, how to convert an FP32 model to Int8 model. For this, Intel has provided the Intel AI Quantization tool for TensorFlow. Here, we provided a fully automated solution to convert a TensorFlow FP32 model to Int8 model. So, what are the basic quantization steps does this fully automated black box Intel AI Quantization tool for TensorFlow do? It basically takes a trained TensorFlow model in FP32, converts it to optimized FP32 file with a .pb extension or protobuf file format, which is the official file format Google uses. Then it takes these FP32 files with FP32 ops, converts them to quantized Int8 ops, and throws out an Int8 pb file, which then is calibrated for all the range values to give out a final optimized Int8 pb file. This FP32 file and this Int8 file is what we've seen earlier while demonstrating Model Zoo, which runs in an Intel optimized TensorFlow environment for latency, throughput, and accuracy run. Let us now look at a short demo of Intel AI Quantization tool for TensorFlow. In the interest of saving time as before, I have pre-downloaded the binary for Intel optimized TensorFlow version 1.14, pre-built with some graph transforms that are used for quantization. I've also downloaded the Intel AI Quantization tool for TensorFlow repo at github.com/intelai/tools and saved it in this folder webinar. To run the tools, I need to first navigate to the tools repo, and then I need to run quantize model.py inside the API directory, specify the model ResNet50, specify the model location of the FP32 graph protobuf file, and the data location of the dataset, which is ImageNet here, that is used for accuracy and the calibration section. So on running it, you would find that the fully automated Intel AI Quantization tool for TensorFlow will take an optimized FP32 KB file and will change all the FP32 ops to Int8 ops, and then go through some fusion of some of these Int8 ops and calibrate them to finally throw out a quantized Int8 PB file. In the process, it also calculates the accuracy measure as shown, top 1 and top 5 accuracy for ResNet50 model using the ImageNet dataset. The Int8 final fuse graph.pb file is also shown, which can be then used with Model Zoo for Intel architecture to run performance runs, latency runs, or accuracy runs as demoed earlier. Now that we have seen how easy it is to take a TensorFlow FP32 model and quantize it into Int8 model using the fully automated Intel AI Quantization tool for TensorFlow, let's open this black box and see what is happening inside in more detail. Post-training quantization, detailed steps. The steps for post-training quantization can be thought of or divided into three main sections. The top section, or the FP32 pre-processing section, the middle section, Int8 quantization section, and the bottom section, Int8 calibration section. Of course, we feed in the TensorFlow model FP32 on the top section, and we received an optimized Int8 FP32 on the bottom section. Let's first look at the top section, the FP32 pre-processing. Here, we take a TensorFlow model in Python. We train the model and obtain a checkpoint with a .ckpt file extension. We also save or obtain an inference graph with a .pb file extension or protobuf called the graph.def. We then, with the checkpoint obtained in step 1, we freeze it or put the values inside the graph.def to obtain a freezed protobuf file with all FP32 ops. Further along, we also do few fusions and optimizations to obtain a final optimized FP32 file. Now that we've obtained the optimized FP32 file, let's move on to the middle section, which is the Int8 quantization. Here, we take the optimized FP32 PB file and we change all the FP32 ops inside it to quantize Int8 ops. To be able to convert the FP32 ops to Int8, we actually introduce a quantize op. Together, we also add a quantize range min and max op. This is so that we can map the FP32 values to Int8. It is to note that the output of convolution operation will take in two Int8 ops and give out an Int32 data type op. To quantize it back into Int8, we introduce a requantize op with a requantization range op to calculate its min and max. So the output of requantize op would be Int8, and hence we've obtained a quantized Int8 PB file. The final step in post-training quantization is this section called Int8 calibration. Here, we take the quantized Int8 PB file and basically run it in the TensorFlow environment so that we can calculate the range values for both requantize op range and the min and max ranges that is used by the quantize op. We also freeze these ranges into the respective ops. That means in the requantization range is basically converted to a const node and fed into the requantize op, and the min and max op ranges are converted to const nodes and fed into the quantize op node. Later, we end up doing further fusion of these quantized ops and also strip any unused nodes so that we finally obtain the Int8 optimized PB file. Now, let us remove the curtain and see what really happens at the graph level. In this slide, we are seeing the graph view of FP32 preprocessing section. So as we've discussed earlier, we take a TF model in FP32 and we freeze the values of checkpoint onto the freezed FP32. The graph of freezed FP32 for a ResNet 50 model would look like this, where a convolution node will be followed by a fuse batch norm node, which will be followed by a ReLU node. The filter, which is a const node to convolution, is represented in white, and the other const nodes to fuse patch norm, such as scale, offset, mean, and variance, is also represented in white. We do several FP32 optimizations to this freezed FP32 to obtain a freezed optimized FP32. One such optimization is called a batch norm folding, wherein we take a fuse batch norm node and we fold it onto the convolution node above it and a bias add node below it. This is shown in the diagram on the right. Hence, these fuse batch norm folded graph here represents the final optimized FP32 PB file. Let us now look at the graph view of the middle section, which is the Int8 Quantization section. Here, we start out with the final optimized FP32 PB file, and we actually change all the FP32 ops to quantize ops. So here you see that the max pool is now quantized max pool, and the convolution 2D is now quantized con 2D. We've also undergone some fusions to fuse the quantized con 2D with bias and ReLU. Next, we introduce a quantize op so that we can convert or map the FP32 values to Int8 values, as shown in the diagram here. For these quantize ops, we also add a min and max op so that we can calculate the ranges. As a next step, because convolution 2D's output is Int32, for quantizing it back to Int8, we introduce the requantize op, and we also introduce the requantization range op, which calculates the range of requantize. The output of this is naturally the quantized Int8 PB file. Finally, we are going to look at the graph view of the Int8 calibration section. Here, we start out with the quantized Int8 PB file, run it using Intel optimized TensorFlow so that we can calculate the ranges of requantization range op, freeze it so that it is a const node for the requantize op. We repeat the same thing wherein we run the model and we calculate the ranges of min and max ops and we freeze it, making it a const node for the quantized V2 op. Finally, we undergo with some fusion so that we fuse the quantized con2D with bias and ReLU with the requantize op and also strip any unused nodes, getting the final optimized Int8 PB file. To conclude, let us look at some key takeaways from this webinar. Quantization is the usage of low precision data types, such as Int8, to represent higher bit depth numbers, such as FP32, to achieve higher throughput and lower latency with minimal loss of accuracy. Intel optimization for TensorFlow is available through many distribution channels. You can find the installation guide at software.intel.com, articles, Intel optimization for TensorFlow installation guide. Model Zoo for Intel architecture contains several pre-trained TensorFlow models and serves as a one-stop location for you to easily run TensorFlow models for throughput, latency, and accuracy. You can grab this from github.com/intelai/models. Intel AI Quantization tools for TensorFlow provides a very easy to use tools to quantize TensorFlow models from FP32 to Int8. You can grab this from github.com/intelai/tools. As mentioned before, Intel has also provided Docker containers for Intel optimization for TensorFlow, and we've also demonstrated how easy it is to install in cloud environment such as AWS or GCP instance. In the end, I would like to thank the extended TensorFlow direct optimization team, the Intel Deep Neural Network library team, and the webinar team, especially Meghna Rao, for hosting and coordinating this webinar. Thank you.